Hi, everybody. Welcome to the DevNation Tech Talk. Today we've got a couple of engineers, although they asked me to refer to them as superheroes, to talk about observability on the OpenShift side and some really cool stuff that's coming. Guys, if you want to introduce yourself first of all, Pavol.
Yeah, hello everyone, and hi from Switzerland. I'm software engineer.
And
there will be as well introduction in the slides.
Always likes to do a little intro so I remember who it is I'm actually talking to. Do you want to share your screen, Pavol? And I'll hop in.
Yeah.
Cool. I'll pass it over to you.
Okay, thank you very much. All right, it seems to be loaded. So again, hello everybody, and today I will be talking about observability, and with me is Ruben, and we would like to essentially kind of show you how easy it is to deploy end-to-end distributed tracing infrastructure with Grafana Tempo and OpenTelemetry operators. And just quickly about myself, again, software engineer, I working on the observability technology, so I contribute and maintain part of the OpenTelemetry, Grafana Tempo, and Jaeger ecosystems. And when I'm not working, I'm based in Switzerland, so I love to spend my time in the mountains. I do awesome e-bike riding and freeride skiing. If you would like to talk to me after the presentation, you can do that on the CNCF Slack, or you can find me as well on Twitter. Ruben, would you like to introduce yourself?
Yes, thank you, Paul. Hello, I'm Ruben Vargas. I'm from Mexico. I'm a contributor to Tempo, Jaeger, and OpenTelemetry. I would like to spend time with my family in the beach because I have the beach near here. You can reach me also in Slack if you have questions after the presentation.
Okay, thank you, Ruben. And I'm definitely jealous of the beach because we are going into winter and it's going to be cold again. Okay, so what I'm going to talk about, first of all, I would like to do introduction to distributed tracing by explaining you differences between metrics and logs, because with that you will understand what tracing can bring you as value. And then I will show you, what stack you can deploy on OpenShift to deploy end-to-end tracing infrastructure, but as well on Kubernetes because these operators are shipped on vanilla Kubernetes as well. And we will use them in a live demo where I will deploy microservice-based application and instrument it with OpenTelemetry, and we will see, live tracing data coming to my Jaeger console. I will explain how the data look like and what value you can get from the Jaeger console, and as well some cool features with metrics. And after that, Ruben will take over and he will talk about the technical stuff about the operators. He will explain how the CRDs work, and he will go more into the details of what each operator can give you as a capability. And at the end, we will do Q&A. Okay, so the introduction. So when we start writing our first program, we usually write our hello world, which essentially prints a log statement into the standard output, right? The hello world. And it is a log message in an essence, right? It gives user some information what happened in that program. So logging is something that everybody is familiar with, and log messages can give us a lot of value and a lot of insights into our applications. However, there is no standardization in logging, and therefore different people, different developers, different languages, different application runtimes use different logging messages and different styles for the same events. So for instance, for HTTP requests, some framework will put URL into the log message, some framework will put just the path, and things like that, right? So there is no standardization. And with modern distributed systems, it's even bigger problem because we are using polyglot deployments, we are using multiple frameworks, and then if we want to analyze logs on scale, it's problematic because we need to understand each particular service, how the logging is used in a service. The other problem is there is no correlation in logs, right? If you need to correlate logs from multiple machines, there is no standard key that we could use to correlate these messages together. And this all leads to the cost, right? As there is a lot of logs being used, the cost of logging solution can be quite high. But it depends, of course, how you do your logging in your organization. On the other hand, metrics are very different. Then they don't give us any context, right? Metric is just a numerical value that gives us immediate feedback how a system is behaving, right? Which is great as well, because we can use the metrics in our alerting systems and get quickly notified if something goes wrong. So that's metrics. And so what's traces, right? And traces are, in my opinion, very similar to logs with a couple of key differences. They are structured, and there's as well standardization. We will see that in a demo, but by standardization, I mean, if there is an HTTP request in my Golang application, tracing infrastructure will log the same data as the Java and Node.js application. Therefore, it makes it super easy to analyze traces in a polyglot distributed system. And additionally, tracing is highly correlated, right? Tracing, we can correlate all these spans together and construct you end-to-end view what happens with a request in distributed system. We will see that in a demo in more details. Just to summarize, you can think about tracing as distributed stack traces, right? Stack trace gives you a lot of details of what happened in your application, but with distributed tracing, you essentially get distributed stack traces. Or you can think about it as structured logs with correlation and causality. We'll see that in a demo as well. It's going to be more obvious there. And this is all useful for end-to-end understanding how a single request goes through your distributed system. And you can use that for root cause analysis and performance optimization. So, okay, so what technology we have on OpenShift and as well on Kubernetes to roll out distributed tracing infrastructure? Before we dive into the operators, it's as well important to show you the kind of the high level architecture, and the most important detail that is on this slide is the data collection and the fact that data collection is decoupled from the rest of the system. And that's because data collection is the hardest and the most resource consuming to get done, right? So for instance, if we want to use logging in our application, we need to use the logging API in every service, right? And the same for metrics and traces. Therefore, data collection might require code changes in every single application that we deploy. And if we later decide to change the tracing vendor or backend, we shouldn't touch our applications. Therefore, it's very important to use some instrumentation API that is open, that is well standardized and stable, so it doesn't change over time. So for data collection, we recommend using OpenTelemetry, and for storing the data, we at the moment working on a Grafana Tempo operator that stores the data in the object store. And for visualization, we are shipping Jaeger console. We will see that in a demo as well. So the first operator is the OpenTelemetry operator, but an OpenShift, you can find it as Red Hat OpenShift distributed tracing data collection. It has essentially two capabilities. It deploys OpenTelemetry collector as a sidecar deployment or daemon set, or it can instrument your workloads by injecting OpenTelemetry auto-instrumentations or agents into your workloads without any code changes, right? And this is confusing. I told you that you have to do code changes to your application if you want observability. It's true to some degree, but you can get along without any code changes if you don't need any customization. We will see that in the demo as well. And the second operator that I'll be using is the Tempo operator. And it essentially deploys Grafana Tempo in the microservice mode. And the main capability is that it hides the Tempo complexity, Tempo configuration complexity, because the upstream project has so many configuration options. And so what we created is something opinionated for the Kubernetes environments that gives you only a subset of configuration options that make sense for Kubernetes. And then as well, the operator gives you additional features like authentication and authorization. I think Ruben will be talking about it as well. Okay, let's jump into the demo. So what I have prepared here is a microservice application that you can find on GitHub under my account, Pavol Loffay, and then I think it's pinned to my main page on GitHub. But essentially, it's a microservice application. It consists of 3 services: front-end, backend 1, and backend 2. Front-end is Node.js application. Backend 1, I think it's Python or Java, and backend 2, it's Python or Java as well. So what it does, essentially, the front end receives a request to roll a dice for 2 players, and then it forwards the request to backend 1 and backend 2, which returns the numbers, right, from 1 to 6, and then the front end decides which number is bigger and prints the winner. It's very simple. So what I'm gonna do right now, I'm going to deploy it to my OpenShift cluster that is running locally. And as you can see, the pods are starting. And on a separate tab, I'm going to pour forward the front-end application. And as you can see, there is as well a load generator that creates requests against the front-end service. Unfortunately, it takes some time to deploy these containers. It should be ready pretty soon. And after it's deployed, I'm going to jump into Jaeger console and show you that this application is not reporting any trace data to Jaeger. Okay, so backend 1, backend 2 are up. We just need to get the front end. Okay, front end is up and running as well. I can do the port forward. And yeah, essentially this is the front-end application. Player 1 rolls 5, player 2 rolls 1, so player 1 wins. Super simple. If I go to Jaeger console, as you can see, it's not returning any data, right? Because these applications are not instrumented. They don't contain any OpenTelemetry agents. So what we're going to do right now is to instrument them. And instrumentation is actually very simple. we need to just apply the instrumentation CR from the OpenTelemetry API version. And this CR essentially contains the endpoint where trace data should be sent, which is my OpenTelemetry collector in Observability backend namespace, and then some sampling configuration and everything that needs to be configured for the OpenTelemetry SDK. So I'm just going to apply it to the cluster. You can see it has been created. The operator applies some of the default options, so you see more data here, but it's essentially the same as I showed you on the previous slide. So when I did this, the applications are still not instrumented. Actually, nothing happened. If I do get pods, you see they have been running for 3 minutes, and they are still not instrumented. If I go and refresh the application and then refresh Jaeger, there is still no tracing data. So actually, to finish the instrumentation, I need to apply annotation to the deployments, to the pod specification of the deployment. So for front end, we're going to apply OpenTelemetry instrumentation annotation inject SDK, which is going to instruct the operator to inject OpenTelemetry SDK configuration to this pod. The front-end application has been instrumented with the OpenTelemetry API, but the SDK is not configured, so the application is essentially not instrumented. It's not sending any data to the tracing backend. Right? It's like no operation instrumentation in this case. So we're going to apply the annotation and see the pods, and we can see we change the pod spec, so the front end restarts and it's up and running. I'm going to finish the instrumentation by annotating the backend one with the inject Python, because it's a Python application. In this case, again, the pod will restart because we are changing the spec, and the OpenTelemetry operator will see that it needs to instrument it and will inject the Python instrumentation libraries into this deployment, and as well configure the SDK. And last, the backend 2, which is a Java application. See, it's restarting as well. And we see there is an init container. And the init container, it contains the OpenTelemetry agent or instrumentation libraries. And it's copying them into an empty dir volume that is mounted to my application container. And then the application container will use it because the operator as well configures the Python and Java runtimes to pick it up. Okay, so that's up and running. I need to port forward again because the pod restarted. And let's see, the application is up and running fine. And now in the Jaeger console, we should see trace data coming to this backend. And we see 3 services, backend 1, backend 2, and front end. Let's just choose the first one. If I click on Find Traces, the Tempo deployment will search in the object store the traces that have been reported, and essentially see all the requests that went through my application. I can even choose the slow ones by clicking on these bullets. So maybe I can choose this one, and this is the trace view, the most important view from the tracing system. And it is essentially a Gantt diagram or timeline view. And it helps me to understand end-to-end what happened with the request, right? So each line represents an operation in a system. So the first line is the first HTTP request processing by the front-end service, and the last one is, or this one is the HTTP processing of the backend one service. And by looking at the screen, I can clearly understand where the time is being spent, when this request is sent to my distributed system. Also, this solid black line is important because it denotes the critical path, right? So if I need to optimize all these requests, these distributed requests, I should optimize the operations that are on the critical path to bring the overall latency of 138 milliseconds to something lower, right? So, okay, by just looking at this, I understand, where the time is being spent and what can be optimized. In this case, it's not maybe a good example, but in some cases, you see like staircase pattern where it immediately shows you that some operation is done in serial that maybe can be done in parallel, or you see a lot of operations done in parallel that can, affect your performance. Okay. So next, I'm going to click on the operation, and what I get is the information about this particular operation, right? And this was an HTTP request. I can see that from the tags or attributes. I see information like, what is the HTTP host? What is the status code? What is the URL? Essentially, all important HTTP data that can help me to understand this request. And if I choose the HTTP request from the backend one, I see exactly the same, right? I see the same HTTP attributes. What is the route? What is the method? What is the URL, right? So frontend is Node.js application and backend one is Python, but we get the same information about the same event in the system, right? Which is HTTP request. And the second, what I can show you here is the process. And the process essentially tells you from where the data is coming, right? So in this case, it's a Kubernetes container. It's coming from this deployment, namespace, pod, and node. We can as well see, what is the process command line and what is the Node.js version and things like that. For the Python application, we'll see, different deployment, and then the information that this is a Python service. Okay, and at the beginning I was talking about logs, right? Like how logs are sort of similar to tracing, but they are not structured, they're not standardized, and there is no correlation and causality, right? So maybe we can jump into the OpenShift console and take a look at the front-end logs. And what we'll see here is a bunch of data, right? And we even see, what is the trace ID, because we are putting the trace ID into logs. But we see, some of the HTTP information, right? What is maybe the URL, what is the status code, and things like that. But the logs are much harder to understand than traces because there is no standardization, and we cannot easily correlate these logs from the logs from other applications, right? So if I go and see the backend 2 logs, there is as well some good information here, but it's different to the front-end application. Okay, so we use this screen if you need to understand a request end-to-end. And then what I wanted to show you is the monitor tab, which is super cool. And what it does essentially is it shows you metrics that are derived from traces. And it shows you the same set of metrics across the services, right? So for backend 1 and backend 2 and frontend, we are getting the same latency, error rate, and request rate metrics. And then if the application has more operations or more endpoints, we will even see the same metrics for different endpoints in that application. It's super cool that this works automatically on trace data, meaning that the collector is receiving only traces, it's looking at the trace data and it's deriving these metrics from traces. So I didn't have to write any, metrics instrumentation by myself. I just used, the trace data that is coming from these services, and I was able to get these metrics. I can further use them in my alerting system. Okay, so this is all for the demo. Let me jump back to slides. And Ruben will continue with talking about the architecture.
Hey, hello. Thank you, Paul. I will share my screen. Okay. Okay. What I'm going to talk today is about the architecture of the observability solution that Pavol already demoed. And this essentially used two main projects, two main open source projects for doing that possible. One is OpenTelemetry, which is essentially a collection of SDKs and APIs and specifications. And also it has the OpenTelemetry collector component, which is in charge of collecting all the signals. In this case, we are collecting the traces. For the instrumented part, we use the SDKs and APIs that I mentioned. But OpenTelemetry itself is not capable of storing or querying the things. It's just in charge of how to generate those signals and how to collect it. In order to have a place where we can generate when we can store those metrics, those signals, we need something else, and it is where Tempo comes in. Tempo is a backend storage for tracing that essentially use an object storage, which makes it simple and scalable. So overall, the architecture is composed of these components: the instrumented application that we need to instrument in order to generate the traces, the OpenTelemetry collector, and the Tempo component, which uses a object storage to store the information in a more permanent way. So in order to do that, I forgot to mention that OpenTelemetry has its own operator and Tempo has its own operator. These two operators are gonna help us to easily deploy this on OpenShift or on Kubernetes. So first I'm going to describe Tempo, or backend backend storage system. And this is the overall Tempo architecture. We have in the blue lines are the write path, which is in charge of receiving the traces and write it to the object storage. We have the distributor. The distributor, as its name says, it receives the traces and distribute all the information across the ingesters, because we could have more than one ingester replicas. So the distributor only receives that and split the work across all the ingesters that we have. And those ingesters are in charge of creating blocks of data, and each n seconds flush it to the object storage. So the ingesters receive the data and store the data for a period of time, and after that period of time, it will flush the data to the S3 or to the object storage. In the green line, we have the read path. This query is actually in charge of executing the query and fetch all the objects from the object storage or the blocks. And because the ingester also have data, it needs also to take data from the ingesters. Those ingesters are communicated by the ring, so they know each other how to split the work, and also the query know to which ingesters needs to ask for more information. And finally, the query front end, which is the API that is exposed. The Tempo has this own REST API, and this API also supports TraceQL. And as you can see, the distributor is able to ingest queries from OpenTelemetry or OTLP protocol, but also from Jaeger protocol. And the query front end, you can connect this query front end as a data source for Grafana, but also there is a plugin for the Jaeger UI, which is the UI that you saw in the Pavol's demo. There is a plugin that it communicates to the Tempo API and serve the correct answer to correct reply to the Jaeger UI. And finally, we have the object storage. The object storage could be S3, GCS, Azure. So those are the compatible object storage that Tempo currently works with. And well, this is the overall Tempo architecture. Now we have also the operator that allow us to deploy all of those things in Kubernetes, so we don't need to do it manually. So first of all, for deploying Tempo, we need to create a secret. The secret is gonna contain the information relative to the object storage. But for example, in this case, we are using Minio, which is an S3 compatible object storage. And we need to set a couple of data. In order to connect to the S3 storage, we need to provide some data to Tempo. And in this case, it's the endpoint, the bucket, and the ID and secrets. So Tempo can go and connect to the object storage and authenticate it to it and know which bucket it's gonna use. We need to create a secret. In this case, the name of the secret is Tempo storage. With this is the first step. And the next step, when you install the Tempo operator, it creates a new CRD. Not the kind, is Tempo stack. And this Tempo stack will deploy all the components that we saw in the previous slides. It deploys the distributor, the ingesters, the query front end, and also do the configuration to connect to the object storage. In this case, we are specifying the name of the secret that we already created that contains all the information to configure the connection to the object storage, and we need to specify the type, because as I mentioned before, we support different types of object storage for example, S3, Azure, DCS. And then we have a couple of options that allow us to configure different components. For example, for the query front end, we can enable or disable the Jaeger UI. If we want to have the Jaeger UI deployed along with the Tempo, we can enable it and it will be deployed. We can also specify if we want to expose it as a route on OpenShift or as an ingress, as a regular Kubernetes ingress. We also have other interesting features. In the right side of the slide, you can see other interesting features, like for example, the gateway. The gateway is a special component that allows you to support authorization and authentication, and also multi-tenancy. In this case, I'm configuring the tenants and I'm using the OpenShift authentication and authorization mechanisms to 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 do the things, but it could also support OpenID Connect protocol standard. If you enable it in another mode, there is a static mode, and you can configure other things in order to support OEDC. And also, the other interesting thing of the operator is it is able to create service monitors, so you can monitor the tempo stack, and also rules for the alerts and promises. The other component that I want to talk about is the OpenTelemetry collector. Note that we already have the backend deployed. We have a way to store or traces, and we have a way to query the traces, but we need a way to collect those traces. And this is what the OpenTelemetry collector does, as the name says. How the OpenTelemetry collector works, essentially, is a pipeline. It's a data pipeline that consists of mainly 3 components. The receivers, which are the input. You need to specify how are you going to receive the data. For example, for the logs, could be that you are going to watch a file for changes, but usually, in the case of traces, you this OpenTelemetry collector open a port and expect the data in some format. For example, here we have Jaeger, OTLP, ZipKing, which are protocols for tracing that OpenTelemetry already supports. Then, one of the interesting parts of this OpenTelemetry collector are the processors. Once you receive the traces, you can do interesting things with them. One of the things that you can do is batching. Batching is helpful because you don't want to send trace by trace, span by span to the exporter. You want to batch it before sending it, but you can also filter it by attributes, add new attributes, modify the existing attributes, or for example, in the case of the demo that Pavol did, you can extract more information. And finally, because this OpenTelemetry collector is used for collecting and processing the data, we need to export to some other place. And it's the same for the receivers and for the exporters. We have different protocols that we can export with. In this case, we are using, because if you remember the slide of the Tempo distributor is able to receive OTLP and Jaeger. So we can configure these exporters to export to OTLP, so it could be received by Tempo and stored in the system. OpenTelemetry also have its operator, and the operator allow you to deploy this collector easily. And we have this CRD. For example, the operator introduced this kind, which is OpenTelemetry collector, and we have different configurations here. We have the receivers, and as I mentioned, this is for example, configured to receive the OTLP protocol. We have the exporters, and the exporter, in this case, we are exporting to Tempo distributor. So this configuration will receive traces from the application in OTLP format and forward it to Tempo distributor. But we have the processors that in this case, for example, I configured the batch processor, which, as I mentioned, it batched the traces before sending it to Tempo. We also could have, for example, one interesting processor is the Kubernetes attribute processor, which this processor takes information from the context. It could be, for example, in this case, the connection between the pod and the and the collector. It could take the metadata, and it could append information to the span. For example, the pod name. If the pod belongs to a deployment, it could attach the deployment name, the node of the Kubernetes, the cluster name. and other useful information that you could have available in the spans in order to have a better understanding of how the system is behaved on Kubernetes. Then we have the service, which is the glue of all of the three things. And you have the pipelines, the different pipelines, because this collector, we are focusing on traces, but also this collector handles logs and metrics. And we have this trace pipeline. In here, we define the receivers, processors, and exporters for that pipeline. And now there is one other thing, because we already have, for example, here we define two pipelines, which is the traces and the metrics. But why we define the metrics? Okay, we define the metrics because there is a connector. The concept of the connector is that you can connect one pipeline with another. In this case, we are connecting traces to metrics. And we are using this span metrics connector to generate the metrics that you saw in the Pavol's demo, and the red metrics. That's why we use this connector. And last but not least, the instrumentation. We already have these backends to store the traces, which is fine. We already have a mechanism to collect, but we need to generate information from our application to the OpenTelemetry collector, to the system. But there are two ways of doing this. Manually, explicit, you have better control, you could have better performance, but the disadvantage is you require code changes. And the other way is the auto instrumentation. It's easy to roll out, cover a lot of frameworks, but you don't have control. You are going to see spans, for example, for the gRPC request, for the database connections, but for business specific things, you need to instrument manually. This is how manual instrumentation looks like. This is a fragment of a Go application. And you can see that you need to inject, to write code in order to have the information. And you need to start the span, you need to end the span, you need to add your attributes manually in each function or in the piece of code that you consider you need the information. And well, you need to recompile the application and redeploy it, and it could be a resource-consuming process. So we have another way, as I mentioned, which is the auto-instrumentation, automatic instrumentation. This captures the telemetry data for popular libraries and supports different languages. Supports Java, .NET, Go, Node.js, Python, and it has some different mechanisms depending on the language to inject the code. In this case, I'm going to talk about the Java agent, but there are similar things for other languages like Python or .NET. As I said, we have two mainly operators deployed, the OpenTelemetry and the Tempo. And the OpenTelemetry is not just for deploy the collector. It could also provide another CRD, another kind, which is instrumentation. We can create a instrumentation resource with different things, like, for example, in which endpoint we are going to report the metrics, the samplers, some environment variables, and some options that we can set to this auto instrumentation CRD. Once we create this CRD, we need to annotate our pods. This is how the pet clinic, the application that Pavol showed you, well, no, this is another one, I'm sorry. this is how a deployment works, look like, and this is the notation that we need to add. As you say, this is the name of the instrumentation, CRD, and this is the notation. This last part of the notation indicates to the operator that we are going to inject Java out the instrumentation, and this is the name of the instrumentation that we create in the previous step. And the other things are regular deployment stuff like the containers and labels and other things. How it works, this attach a new empty volume to the pod and an init containers that will copy the Java agent from this volume to a mounted from the image to the mounted volume, and also we add some environment variables like the Java options in order to load the Java agent when the virtual machine starts. How this Java agent works is like when the application starts, it loads the Java agent, and the Java agent start looking into the classes and inject the code in the classes that needs to be injected. This is how it looks like in YAML. We have these containers in the pod, regular with environment variables and the modes and the image of the application. Once the webhook mutation mutate this pod, because the operator see that it have the annotation, it will mutate the pod and will add this init container. You can see the command that is essentially just copying jar to another path, and this path is the mount, is the new volume that it's created, and also it adds the Java tool options. This Java tool options is for so the Java virtual machine will be able to load the Java agent, and the other are the options defined like propagator, sampling, and other stuff that we already defined in the instrumentations here. And with this, we already have the three main components of our architecture. We already have the application instrumented, the collector, and the tempo, which is the backend for store and query the data. And with this, we have our solution completed. Yeah, that's all for me. I will give the control to Pavol again.
Okay, I will share my screen again for the wrap up. And yeah, we talked about many things, but one of the important things I want you to remember is that the deploying tracing infrastructure with operators on Kubernetes and OpenShift, it's not hard. It's actually pretty easy. You need two operators one that can deploy the backend and one that can help you with instrumentation and collecting the data with all the processing capabilities needed for PII, maybe attaching new attributes from Kubernetes environment and things like that. So it's pretty simple. What we as well seen is the instrumentation, the basic one, doesn't require any code changes, and you can as well extract metrics from trace data. And with that, I think where we are going is a place where observability will become part of the platform, and we as developers will not do any kind of hard work to get the observability and monitoring up and running. Okay, let's do the Q&A. I already see one question in the chat. I will read it out. So can we correlate trace IDs in logs? Yes, we can. And use the OpenTelemetry instrumentation can be configured to put the trace ID into the logs. So for instance, if in Java, if you are using, let's say log4j, there is a log4j instrumentation that will put the trace ID, span ID, and sampling bit into all log messages. And then there is a second part of the question. If yes, do we need to have OpenTelemetry SDK in our services to access trace IDs? Well, usually the OpenTelemetry SDK doesn't access trace ID. It generates it, and it can as well put this ID into the log messages. Okay, I think there is a second question. How does the trace work across different components with multiple pods? Do you mean ports or pods, like the Kubernetes pods? I think the person meant the Kubernetes pods. Well, it's the demo that I showed you, right? I deployed 3 pods that were using different languages, and the trace, essentially what happened under the hood is when the front-end service receives the request from user, it generates trace ID and span ID and the data needed for the first span. Let me go back to my search screen. The front-end service will generate the trace ID and will create this first span. So this operation, this line, is called span in a distributed tracing. And then when the front-end service calls backend, it will inject the trace ID, the span ID, and the sampling bit into HTTP request. And then the next service can read it from the headers and continue same trace. That's the concept behind distributed tracing.
Also, just a quick question from me as well on this one. The operators that are required for this, the Tempo operator and the OpenTelemetry operator, they're both fully supported Red Hat operators, aren't they?
Yes, so they are in tech preview as of now.
Right, okay.
And yeah, people can use them, can find them, on OpenShift, on the OLM, but as well on the Operator Hub. So yeah, there are 2 distributions.
And you mentioned that they're actually in the future probably going to be part of the core product rather than optional operators.
It depends what you mean. They will be optional for OpenShift.
Right.
I don't think there are plans to embed them into the core OpenShift, but yeah, they are layered products.
Okay. I think there was one more question on the chat.
Yeah, I see that there's. So the question is, what if I have 2 pods with front end? Okay, so you scale the front end to 2 instances, and the tracing will work in a similar manner, right? The replica that will receive the request will generate the trace ID, and then it will again propagate it to all downstream services. If you have a load balancer in front of your front end, the load balancer can as well start tracing by generating first trace ID and span ID and generating the first span from the load balancer and send the trace ID and span ID to the front end application or to any service that is behind the load balancer. Actually, we can talk about Envoy, which is sort of a load balancer. Envoy can as well create spans for any incoming and outgoing requests. And but the application still needs to propagate the context, the trace ID and span ID from inbound to outbound request. So you can still use the OpenTelemetry instrumentation CR to help you with the context propagation, but use Envoy for generating the edge spans, for receiving and outgoing HTTP requests. There is a second question: how does the performance look like with on-premises OpenShift cluster with AWS S3 storage backend? Yeah, I think it's a very broad question to our topic today. Maybe if you could provide a bit more details, be a bit more specific.
Is that to do with the latency impact of talking to remote S3 storage from an on-prem cluster? I would assume so. Is that something that factors into the performance? Yeah, the latency.
I think we haven't tested this specifically. It would impact the Tempo deployment, right? How Tempo can store data into S3 and how it can read it. I don't have any specific data that I could talk about right now.
I say everything within the system is time-stamped, isn't it? So you do get an indication of timestamp.
Yeah, so every span has a timestamp, right? Go to Jaeger console.
And that timestamp is source, not the time it was stored on disk.
Exactly, it has to be the source. And it's as well, like we are monitoring distributed system, right? So there is a clock skew issue. So we have to be careful with looking at these timestamps. They might differ from one service to another. Okay, any more questions?
I think that's it, and I think we're coming up to the hour. I'd like to say thank you to both you guys for that. That was really cool. Again, if you want to tune in next month, there'll be some more stuff to play with. There's a link in the actual bottom bit showing you a link to a nice blog post from Pavol. Anyway, thanks for that, and cheers all.
Thank you.